This is the story of How to Deflect an Asteroid by Rick DeWitt, mad scientist. The spacecraft artwork and the asteroid artwork was done by Bill Nye the Science Guy, lifted out of his video and altered by Rick to tell a different story. Okay, let's say that we wanted to deflect an asteroid using a gravity tug. We would use the weight of the gravity tug next to the asteroid to pull the asteroid along, to make it speed up or slow down just a little bit. A is for asteroid, C is for craft, and the next thing saves the planet. B is for ballast. Ballast is some mass that we grab off of the asteroid and place onto the craft and mechanically stow it. The ballast is obtained out there next to the asteroid instead of being launched from Earth. So this is a way to increase the mass of the spacecraft by borrowing a little bit of mass from the asteroid. That works because the gravitational pull goes by the product of the mass of the craft times the mass of the asteroid. So if you change the mass of the craft a little bit, you can pull a little harder. And it turns out that the thrust that the spacecraft can exert is exactly the same as the weight of the craft over the asteroid. That relationship, knowing that the thrust equals the weight, gives us a way to solve the physics problems and find out that ballast is really the only thing that matters. So here's the executive summary of what we're going to look at. First off, we're going to try to change the momentum of the asteroid. But it turns out that that momentum change is only a function of the ballast and not a function of the exhaust velocity. The exhaust velocity, that's how fast you throw the stuff out the back end of your rocket. That determines the power that you use and the amount of mass that you throw, but it does not, in the case of a gravity tug, it does not determine how much delta V you're going to give to the asteroid. The lesson at the end of this whole thing is that to save the planet, we just need to throw rocks. Okay, so to explain this, first we're going to draw a picture. Here's the asteroid, here's the spacecraft, and the spacecraft has some ballast. In order for the spacecraft to work as a gravity tug, the thrust that it gives out has to go on a cone, because if it hits the asteroid, then it won't thrust very well. It'll impinge on the asteroid and you'll lose all that thrust. So we have the angle of the cone is phi. The exhaust velocity is given by the vector u. But the effective velocity of that exhaust is diminished by the cosine of phi. So we're going to use this symbology to do the physics. Now, the physics we're going to use are Newton's first law, Newton's second law. We're even going to throw in Newton's third law a little bit, but it's not shown here. Newton's law of universal gravitation and the rocket equation. You'll notice that in Newton's second law, this term is called the thrust term. It's the velocity of the exhaust times the mass flow rate. We're going to go solve for those. First off, if we're hovering, we know that the sum of the forces is 0. This is if the craft is hovering over the asteroid. The sum of the forces is 0 because it's just hanging there in mid-space. So its acceleration, dv dt, is 0, and the force of the rocket has to equal the force of the gravity, but oppose it, of course. So we can look at the weight of the laden craft, the craft laden with ballast, as the force of gravity by Newton's law of universal gravitation is the mass of the asteroid minus the ballast, and the mass of the craft plus the ballast multiplied together and plugged into the equation. The thrust component of the rocket is given by Newton's second law, which is all spelled out in its full detail here. But there's something very interesting going on with this asteroid. We're accelerating at a very, very small amount. The asteroid almost isn't accelerating at all. So we can actually take the limit as that acceleration goes to zero to find out some interesting stuff. So we're going to start here with the hovering idea, and we're going to move on to the mass flow rate. We want to find that mass flow rate because if we know that, then we can figure out what the rocket equation says. So if the acceleration is zero or approaches zero, then the only thing left for the force of the rocket is the effective velocity of the rocket times the mass flow rate, which is just the velocity of the exhaust diminished by the cosine times the mass flow rate. Well, this force of the rocket equation we can bring down here. To solve for the mass flow rate, we divide by minus u cosine phi, and then we notice that the force of the gravity opposes the force of the rocket. So we can just substitute that in. And then write down the mass flow rate using the full expression of the force of gravity. So we have an expression here that tells us what the mass flow rate should be in order that the ballasted laden craft hovers above the asteroid. Okay, so if that craft hovers above the asteroid and maintains the same thrust over time, we can calculate the delta V. And we just plug that into the rocket equation. We see here the rocket equation is the original mass divided by the new mass. So over time, the mass diminishes according to the mass flow rate. We take the natural log and multiply by the effective velocity. That's the rocket equation. That's what tells you how fast the rocket is going to accelerate. We can, since we solved for the mass flow rate, we just plug it in and we get this big, huge equation that tells us how the delta V is going to change, how the momentum is going to change. Now we can pull that apart and figure out what we can get out of this huge equation. So over here we start with a goal of a certain change in velocity over an amount of time. And that equals this whole big equation over here, expression. Well, certain of these things are constrained by the problem, and certain variables are adjustable. So our engineers want to know what we can adjust and what's constrained. Well, geometry constrains the cone angle. Geometry constrains the cone angle because the asteroid has a certain size and we have to thrust around it. Geometry also constrains how close we can be to the asteroid without hitting it. So the radius, the r squared here, or the distance, is also kind of given by the asteroid, given by the problem. The mass of the asteroid is given. We certainly can't change the gravitational constant of the universe, and we can't launch a very large craft. So the mass of the craft, m sub c, is pretty small. And so that leaves us with just two more things that we might be able to adjust. First off, we might be able to adjust how fast we throw the exhaust, the rocket exhaust. That's u. But it turns out that if you adjust the exhaust velocity, that's balanced by the mass flow. This whole big part under here is the mass flow, and this changes to balance changes in exhaust velocity. The only thing that the engineers get to really decide on is the ballast. It turns out that, and this is the big story, ballast is everything when it comes to using a gravity tug to move an asteroid. Here's why. Ballast is the only thing that determines the weight of the craft, and the weight is the only thing that determines the thrust of the craft, and the thrust of the craft is the only thing that determines the delta V that we're going to be giving to the asteroid, and delta V is the only thing that matters when it comes to saving the Earth. So it turns out that ballast is the key to controlling the ability of a gravity tug to move an asteroid. And that's big news. Okay, so the other big news is the exhaust velocity does not constrain the acceleration. So if you thrust really, really fast, have a high power engine, it'll use a lot of energy and it'll be mass efficient. So it'll use a lot less mass. But it turns out that because we're trying to change momentum, momentum can be changed by throwing more mass with less energy. Because if you throw more mass with less velocity, the energy goes by the velocity squared. So if you throw a lot of mass not very fast, you can develop the same amount of momentum but consume a lot less energy. The problem with most conventional rockets is you've got to launch that mass from Earth. But in the case of moving an asteroid, we have a source of mass. Can you guess where the mass can come from? That's right, the mass can come from the asteroid. So, we can actually make a chondrulic rocket. A chondrulic rocket uses chondrules. Chondrules are the kinds of rock grains that you find on most asteroids. We can pick up those rock grains and throw them as fast as we can, but not, maybe incredibly fast. But if we can throw those little chondrules, we can use the chondrules as propellant mass. And because we've taken the ballast on, we can control how fast or how much thrust we need to use in our chondrulic rockets by how much ballast we take on. Kind of an amazing little balance. The key here is by throwing rocks, we're throwing more mass at lower velocity and saving energy. So, really? Okay, let's take a real example. Let's take 99942 Apophis. And we'll take that as our example and we'll run the numbers and see how that goes. So this asteroid's about 27 times 10 to the 9th kilograms. Its diameter 325 meters maximum. And let's say that we wanted to change its velocity by 1 centimeter per year, which is plenty of change to affect its course enough to miss Earth. Okay, we'll assume a thrust angle of 22.5 degrees and design a gravity tug. Look at those curves. These curves tell us how to engineer a gravity tug. The bottom axis is the ballast mass in tons, and the vertical axis is numbers along a logarithmic scale. You can see that here's 1, here's 10, here's 100, and so on. So this is a log graph. Now, I'll show you how you read this log graph to design a gravity tug. First off, we want to change the velocity of the spacecraft by a centimeter per second in a year. So we go to 1 centimeter, read across to the green curve, and we find out that the green curve is the delta V curve, see? So we read across to the green curve, and we can read off how much ballast we need. And it turns out it's about 150 kilotons. So once we know the amount of ballast, we can read all of the other curves. We just read all of them along that 150 kiloton line. We can find out how far we have to hover away from the thing, what the radius of the ballast would be, how much power we're going to use, and how much mass we're going to need to throw. I want you to see two things. One is the ballast radius, 20-meter radius ball of ballast, a big chunk of rock. So this spacecraft is going to be a big round thing, right? But look at that power, 650 watts, an incredibly low amount of power. And the reason that the power is low is that our exhaust velocity, U, is just 147 meters per second. That's like a high-end leaf blower. You know, it's not really blowing the stuff that fast. We can make mechanical things that throw 60 grams per second at 147 meters per second. And when we do that, we can use a little bit of power to move this thing. Now, so this is a chondrulic rocket because we're throwing rocks. So we're not using very much mass. We're using pretty low power to achieve the same delta V. And the key is that we're using the same amount of ballast. But if we use an ion engine, it turns out that we get the exact same delta V, but we burn a lot more power, 130 kilowatts, and use a lot less mass in the form of xenon this time instead of rocks. So the mass flow has gone way down, but it turns out that we're sitting right next to a gigantic source of mass. So why use xenon? Just throw rocks, save power. So the conclusion from the engineering is exactly the same as the executive summary. The momentum change is only a function of the ballast and not a function of the exhaust velocity. The exhaust velocity does matter when it comes to the amount of power that you're going to use and the amount of messiness. So if you have a high power engine that throws the exhaust very, very fast, you don't need very much mass. And if you throw the exhaust much slower, you need to move a lot of mass, a lot more mass, to make that same momentum happen. So the conclusion from the engineering is to save the planet, just throw rocks. So here is a laden gravity tug throwing rocks to save the planet. Thank you very much.